It's my pleasure now to introduce Dr. Grutzendler from, I hope I'm not mangling that too badly, from Yale University, who's going to speak to us on a novel mechanism involved in microvascular occlusion and recannulation.
Thanks very much. So I have a lot of slides, tons of pictures, so I'm going to have to really rush and skip through some slides perhaps. This is the people that have done most of the work. So in this nice image of the postmortem human brain, you can see kind of what people call the neurovascular unit, where you have an astrocyte wrapping end feet and neurons very close. And that's an interest in our lab in general to understand the pathology and physiology of this unit. But today I'm going to talk to you mostly about what happens when you occlude a single vessel. And at the end, hopefully if I have time, a new technology that we developed in the lab recently to image the white matter, myelinated axons in the cortex of the mouse. This has been told by many of the speakers, but of course the brain consumes a lot of energy and has tremendous amount of blood flow compared to its weight, and most of the energy is consumed at different synaptic functions and maintenance of ionic gradients. Of course, this is all maintained by an intricate network of capillaries. However, there's a few features in the brain that are unique. There's no capillary reserve. In other words, every capillary really is perfused at all times, or most of the times. There's no energy substrate storage. And importantly, in studies that we have recently done, the brain is really very quiescent in terms of angiogenesis after P20 in a mouse. There's virtually no angiogenesis, and as determined by BRDU and branching patterns. And also, we've done in vivo imaging with two-photon microscopy longitudinally. Even after 100 days, we relocate the exact same vessels, so we can quantify turnover, loss of vessels, or pruning, and new vessel formation. You can see two-time point images here at different ages, and this is the summary of all the data. From before 1 month of age, you have a substantial formation of new vessels with a substantial component of pruning, and as the mouse gets a little bit older and past 3 months, there's virtually zero pruning or formation of vessels. So extremely stable as determined by 100-day time-lapse imaging with the exact same vessels. Of course, very important feature of small blood vessels is that they're probably prone to occlusion. I postulate that during the lifetime, you have a lot of clusters of the debris in your blood, clusters of cells, particles of atherosclerotic plaques that are constantly showering the brain. And this could be a tremendous source of pathology in the brain. How does the brain deal with that? That's an interest in our lab. Of course, the most well-known system is the fibrinolytic system. We assume that the fibrinolytic system will break down fibrin-based clots, and that hemodynamic forces will sort of flush the clots through the vasculature. But how effective are these? Nobody really knows, and we've sort of done some work on that. And furthermore, what happens when you have junk like this coming from the carotids that are not susceptible to fibrinolysis? How does the vessel deal with that? We developed a model to study this, in which we inject fluorescently tagged microemboli of any particular size that we can filter at very precise sizes to occlude capillaries, terminal arterioles, etc. And they're fluorescently tagged so that we can image them in vivo or in fixed preparations. We use two-photon microscopy. We can get preparations like this one. This is the this is the superficial cortical vasculature, layer 1, and you can see a single clot stock right there. And we do this purposefully, this very sparse embolization, because we don't want to study stroke. We want to study what happens with that particular capillary and the microenvironment around the capillary. We can follow this over time. You can see that indeed is blocking flow here. You can see the flow in the collateral capillaries here. And the first thing we did was a time-lapse image of what we would have expected to happen, which is fibrinolysis. So you see the clot stock at time point 1 here, time point 2, the clot is gone. In this case, we're using a transgenic with a fluorescent endothelium. We assume that this is hemodynamic forces coupled with fibrinolysis. Plasma gets there. We can measure flow by using line scan imaging with a two-photon microscopy. So we know that plasma gets there, even though there's an occlusion there. We know that there's TPA around the clots as we do immunohistochemistry. However, there's a very interesting phenomenon. The TPA actually is up very quickly and then declines rapidly after 6 hours. So perhaps there's an impediment to the access of new TPA to the area. Now, how effective is this washout mechanism? Well, it's quite ineffective, actually. So if you're a clot and you get stuck there, if you're not washed out by 3 to 6 hours, you'll be stuck there permanently, apparently. So there's a high failure rate beyond 6 hours at the microvascular level, 20 micron clots. If you infuse TPA exogenously, you can boost that a little bit 3 hours after the embolization and virtually zero after 6 hours. So there's something preventing TPA from either reaching or acting at the microvascular level. So what is it? So we did time-lapse imaging in a type 2 GFP mouse with the endothelium label, as you can see here. And a very surprising finding is that very rapidly after the embolization, the endothelium reacts, wrapping around clots, sending lamellopodia very rapidly that apparently trap the clot, in some cases almost completely within 6 hours. You can see this in this electron microscopy where the clot is dark, and you can see the endothelial membrane wrapping around it. So we think that this early endothelial engulfment may prevent the washout of clots within the 3 to 24 hours by physically trapping the embolus within. It may restrict the access also of plasma and therefore of TPA, preventing fibrinolysis. And that may explain some of the failure after 6 hours of the recombinant TPA and may be involved in the no reflow phenomenon. So what happens afterwards? If the clot is stuck there, does the vessel do anything? Is there angiogenesis? I can't show you all the data, but the answer is no. We don't think that there is angiogenesis or a compensatory capillary that forms to bypass the occluded vessel. What we ended up seeing is actually in high-resolution confocal microscopy, we start to see material that looks outside of the vessels, pushing the basal lamina here. And we actually did time-lapse imaging now in type 2 GFP mice. You can clearly see the clots that appear to be outside. You can do electron microscopy, and the capillary looks intact. Therefore, it doesn't look like it's a structural damage to the capillary, and the material is outside. This is actually a very robust phenomenon. It actually happens in about 80% of the clots by about 6 days, but it can happen after 1 day or after 2 days in about 20% of the clots. And it doesn't matter what the material is. There's full recanalization of the vessel, as you can see here, as indicated by these lines, which are flowing cells. And the material is outside. If we do long-term time-lapse imaging to look at vessel patency over time, you can see in time point 1, the clot is occluding. Time point 2, the clot is outside. Time point 3, 1 month later, clot outside, and the vessel is recanalized as measured by our line scan imaging. So perfectly intact endothelium and vessel is recanalized. What's the mechanism? So when we do more detailed time-lapse imaging, we see that there's these lamellopodia that stick out and start to wrap around the clot, forming a vesicle, a large vesicle that traps the clot inside, pushing the clot outside. There's some sort of remodeling going on here. There's a lumen, and eventually this gets recanalized completely, and the vessel survives. Here you can see tangential views of a vessel in which you see the clot trapped here, a lumen, and you can see sort of an opening that's either disruption of tight junctions or the formation of a large transcellular pore. We still don't know that. Here you can see images of a clot that's completely wrapped by the endothelium, and when we three-dimensionally reconstruct this image, you can see the clot sticking its head out of the vessel, and when I increase the transparency of this vessel, you can see very clearly the internal sort of envelope, and you can imagine that this clot is going to be pushed out, the vessel is recanalized. What happens when the clot gets out? By electron microscopy, it appears to be wrapped by some sort of perivascular cell processes. When we use the NG2 GFP mouse, which labels pericytes, we can see that the clot is outside and sort of trapped within the pericyte at early stages. You can see it also past the smooth muscle actin layer here. And if you use cholesterol emboli, for example, this upsets very much microglia, which form a quite reactive perivascular reaction there. But if you use fibrin clots, you end up seeing degradation products within microglia, and eventually the fibrin clot disappears. So we propose that there's two mechanisms, one early mechanism, fibrinolysis and washout, and a late mechanism of recanalization that we propose to call angiophagy because it's sort of a property that's similar to a phagocytic process in some ways. So these may be important for different things. I'm going to discuss that in a second, but it actually happens outside the brain. It happens in the heart at the same rate. It happens in the retina. And actually, interesting, happens in the lung too, but there's another property in the lung. It actually crosses not just the endothelium, but it ends up in the alveolar space. Here's some alveolar macrophages. And you can see the alveolar macrophages completely trapping the clots and degrading them. So one could postulate speculatively that this could be a mechanism of clearing debris from the circulation and eventually degrading them or eliminating them to the mucociliary system. But it's a highly speculative statement. We see similar things in the kidney, but I'm not going to speculate too much. We see that clots have entered the renal tubules, but this is we haven't worked this out in detail. It's quite difficult. The anatomy of the kidney is very complicated. So does it happen in humans? We don't have firm evidence, but we collaborate with an ophthalmologist, and by retinal photography at least, this cholesterol embolus looks to be outside of the vessel. And of course, this is much lower resolution because we're looking at capillaries or terminal arterioles by retinal photography, which is substandard, but there's recanalization by fluorescent angiography. Here's another example. Clot outside, vessel recanalized. We're looking at the mechanisms. I don't have a lot of time to talk about this. There's gelatinolytic activity right around the clots. If you inhibit with SB3CT, which is a MMP inhibitor, you slow down the extravasation process. There's also alpha V beta 3 integrin around the clot, so we're exploring the role of this in the process. There's very interesting platelet attachment to the clot, and this could be very important in interactions between the endothelium and platelets in this process. And then we're trying to do some high throughput in vitro screen, although I'm a little bit skeptical again of the in vitro modeling of this phenomenon. And we're trying to develop some medium throughput in vivo approaches and looking at Alzheimer's amyloid angiopathy, how it alters this phenomenon. And so lessons to learn of this part. I need to quickly talk about our imaging. We propose the term angiophagy. The early phases we think of entrapment are deleterious. And the later phases could be important for maintaining macrovascular patency in the long term, and it could be an additional mechanism in addition to fibrinolysis. And of course, there's major challenges to, if you want to translate this, and perhaps we can talk about this later, so I can show you our myelin imaging. So of course, myelin is a highly wrapped series of membranes which have very lipidic, so the refractive index of myelin is higher than the aqueous medium around it. Because of this, it's a highly reflective surface. So we come up with this method in which we can image myelin in vivo, and the connection with the vascular side, at this point, it's because we've heard so much about myelin in the context of vascular disease, so this could potentially be used to study the consequences of microvascular occlusion. We use confocal reflectance microscopy. We combine 3 lasers into one monocolored image. And as you can see here, there's very interesting phenomena that I don't have time to explain. But if you use single lasers, you get a very patchy imaging of myelinated axons. And this has been published already. So it is unambiguous that these are myelinated axons. So you're going to have to believe me for now. But if you put all the 3 lasers together, they complement each other, forming a contiguous image of an axon. The mechanism is probably analogous to thin film interference, which you have seen with water on oil on the road. And this is the type of images that you can get in vivo. This is the cortical layer 1 of the mouse, the PL vasculature and capillaries. So it's a spectacular image of exclusively myelinated axons. This is the type of stack that you can get. You can go extremely deep, actually surprisingly, for confocal microscopy. And this is evidence that not all processes are labeled. These are the myelinated axons, and there's some dendrites here and other axons that are not labeled. We've tested this in human brain. This is a postmortem chunk of human brain, and despite the fact that it was in formalin for 5 years, you can get images that are quite similar to what I show you. So we're not, of course, we cannot use this in a human, but unless the human is in an ICU and has a craniotomy already, but it potentially could be used for perhaps traumatic brain injury and following axonal disruption over time. And this is just a cool image showing the myelinated axons and the vasculature. Thank you.
We have time for a quick question.
So, on your left?
Yeah.
Hi, very nice talk. I have a very quick question. Do you think that the same mechanism may also, of angiophagy, may also be in play when platelet-rich clots form in situ, such as in the microangiopathies?
We haven't formally tested that, but accidentally, I can't explain the details, we've seen that if you form some thrombus, if there's a thrombus, a spontaneously forming thrombus, you see the analogous mechanisms, yeah. So I think it probably extends to a thrombus.
Thank you.
One more quick question.
Jaime, super cool. The question, what's keeping you from conjugating your cholesterol beads with drug of choice and getting it past the blood-brain barrier by injecting it into the bloodstream and letting it get extravasated with this mechanism?
So to use this as a delivery mechanism?
Yeah.
Yeah, I mean, we've thought about this. The only problem is that you would have to embolize at sufficient. I mean, I think it's doable if you have if it's okay to have very sparse emboli. Otherwise, you basically cause a stroke.
Yeah, but if you're going to die from cancer,
by massively
right?
embolizing the brain. So it's not crazy. Maybe it's possible to do something like that, but yeah.
One more question. Great talk. Can you give the size range of particles that you've seen angiophagy active?
So generally speaking, we look at capillaries, precapillary arterioles, but this can occur in vessels up to 50 microns, I would say. We haven't tested beyond that because we use mice, so it's a little tricky to study. But I would say no, because of the muscle and multiple muscular cells. But I think if you have a monolayer of smooth muscle, you can easily go out of the monolayer of smooth muscle.